Hello, today we will be covering part 2 of chapter 7, where we'll look at Sn1 and E1 reactions. Let's look at this following reaction. We have a tertiary alkyl halide reacting in ethanol. Now, since this is a tertiary substrate, we're not going to be able to do Sn2 reactions with this molecule. Since the reagent is ethanol, we're not going to be able to do an E2 elimination reaction either. It's not a strong base. We're still able to form a substitution product and an elimination product from this molecule, but we're going to be looking at a first order kinetics where only the concentration of the substrate is important. So this is a new mechanism that the reaction is going to undergo. The substitution product and the elimination product are formed from Sn1 and E1 mechanisms. Throughout this video, we will discuss all of the variables for Sn1 and E1 reactions and compare and contrast them to the Sn2 and E2 reactions. The mechanism of substitution and elimination in this case both starts at the same step, which is the ionization of the substrate. The leaving group, bromine, is going to leave to form a tertiary carbocation. Since we have a fairly stable carbocation, this will readily occur. This carbocation can then undergo either substitution or elimination reactions. In the case of a substitution reaction, it's going to go through a two-step mechanism. Remember, for the Sn2 reaction, we were both forming the new bond and breaking the bond at the same time. However, in this case, we are first going to break the leaving group bond, form the carbocation, and then in the second step, we'll have nucleophilic attack with the weak nucleophile ethanol. The final step in this reaction sequence is just going to be a deprotonation of ethanol to form the substitution product. The entire mechanism is actually 3 steps, but the last step is just a simple proton transfer. And this type of reaction is called solvolysis, because the nucleophile is also acting as a solvent. Next, let's take a look at the reaction coordinate diagram for this reaction. If you remember, for the Sn2 reaction, there was just one transition state. Here we're going to have multiple transition states and intermediates. The first step is the formation of the carbocation through the loss of the leaving group. This step requires the highest amount of energy and is therefore going to be the rate determining step. The nucleophilic attack and proton transfer steps will occur much more rapidly and require less energy input to get over the activation barrier. Since the rate limiting step requires only ionization of the substrate, we're not going to worry about the concentration in the nucleophile when we analyze the rate of this reaction. The rate is dependent only on the concentration of the substrate, and since this is just one molecule that's determining the rate, we're going to have a unimolecular rate law, and it'll be an Sn1 reaction where we have S standing for substitution, N for nucleophilic, and 1 for unimolecular. So let's take a look at the mechanism again. The first step is going to be loss of the leaving group to form the carbocation intermediate, and then the carbocation intermediate will be trapped by a nucleophile. If the nucleophile is a neutral species, such as ethanol or any alcohol, then we'll need a proton transfer to liberate the final product after the nucleophilic attack step occurs. We can also have an elimination reaction that undergoes a similar mechanism. Instead of a concerted elimination mechanism, where the leaving group leaves as the deprotonation step occurs simultaneously, we're going to have a two-step mechanism. First, we have loss of the leaving group, and then ethanol is going to deprotonate the beta hydrogen to form the elimination product. Remember, ethanol is not a strong base, so we can't undergo E2 elimination, but it is a weak base, and it is strong enough to deprotonate a beta hydrogen next to a carbocation. This is also going to follow a unimolecular rate law, as the formation of the carbocation is the rate determining step. We can compare the reaction coordinate diagrams of the Sn1 and E1 reaction, and what we see is that the rate laws should be the same for both, and the first step of the reaction, the formation of the carbocation, is also going to be the same. The Sn1 reaction is going to have a slightly smaller activation barrier for the nucleophilic attack relative to the elimination reaction. Now remember, whenever we have a carbocation, there are a few things that we have to look at, and the first one is always going to be the possibility of rearrangement. In this case, for Sn1 and E1 reactions, we are generating a carbocation before any of the before the nucleophilic attack or the elimination portion of the reaction occur. So if this carbocation has an opportunity to rearrange, then it will definitely rearrange. For example, in this first reaction, a direct Sn1 product would be here on the left. That's just substitution at the position where a carbocation is formed. However, what's more likely for us to see is substitution at the adjacent position, because the carbocation that forms at this position will do a 1,2 hydride shift to form at this position. The same is true for this substrate below. We're unable to do a hydride shift with this molecule, but a 1,2 methide shift can occur. When a primary substrate is reacted under Salvallis's conditions, we will only obtain the rearrangement product, and this is because a primary carbocation is so unstable. So the second the primary carbocation forms, it's going to rearrange. So let's take a look at this mechanism. We have a primary alkyl halide attached to a quaternary carbon. As soon as the leaving group leaves, the methide shift is occurring in a concerted fashion to form a new tertiary carbocation, which can then react with the nucleophile. One of the variables that we consider when we are analyzing a reaction is the solvent. To review, for Sn2 reactions, a polar aprotic solvent was ideal for the reaction conditions. In the case of an Sn1 and E1 reaction, since we are forming a carbocation in solution, a polar protic solvent will greatly increase the rate due to its high dielectric constant. So for an Sn2 reaction, we want polar aprotic solvents, and for an Sn1 reaction, we want polar protic solvents. And we can further understand this by looking at the reaction coordinate diagrams for the two comparing solvents. In an Sn2 reaction, a polar aprotic solvent is going to greatly raise the potential energy of the starting material, and therefore it reduces the activation barrier needed for the reaction to occur. In an Sn1 reaction, we're not raising the energy significantly of the starting material, but instead we're greatly reducing the activation energy to get to that transition state, and also reducing the energy of the carbocation intermediate because they're stabilized by the polar protic solvent. The better the leaving group that we have for an Sn1 or E1 reaction, then the faster the reaction will occur. Remember, the rate of this reaction is only affected by the concentration of the substrate. And the first step of the reaction is the leaving group leaving. So the better a leaving group we have, the more reactive the molecule will be for an Sn1 or E1 reaction. The substitution pattern of the substrate will also play an important role in determining the rate of the reaction. The more stable the carbocation intermediate that's formed, the faster the Sn1 and E1 reactions will be. Remember, a tertiary carbocation is the most stable of the alkyl carbocations, and a benzylic and allylic carbocation offer increased stability due to the resonance structures that can stabilize it carbocation over additional carbons. In general, a primary or secondary alkyl halide will only undergo solvolysis if a rearrangement to a more stable carbocation is possible. Generally, we'll have tertiary, allylic, and benzylic alkyl halides that are able to undergo solvolysis to give a mixture of Sn1 and E1 products. For a primary or secondary alkyl halide, often you want to consider Sn2 or E2 reactions instead of Sn1 or E1 reactions. It's important to look for potential rearrangements to a more stable product. Similar to an E2 reaction, an E1 elimination reaction is able to produce more than one Regio isomer. Let's take a look at this example. Here we have two different beta hydrogens on our alkyl halide. Depending on which beta hydrogen undergoes elimination, we'll get a mixture of the two products. E1 reactions are going to be regioselective, but we aren't able to use a base like we can in E2 reactions to control the regioselectivity. Beyond the two regioisomers that are possible, it's also possible to obtain several different stereoisomers in an E1 reaction. An E1 reaction will generally give the most stable alkene as the major product when we have multiple stereoisomers obtained. Recall with an Sn2 reaction, the stereochemistry that observed was always an inversion of the stereochemistry due to the nucleophile having to approach from the backside of the leaving group. In an Sn1 reaction, this is not the case because we're forming a carbocation intermediate, which is going to destroy any stereochemical information. We're going to obtain both the retention and inversion of stereochemistry products in an Sn1 reaction because the nucleophile will have the opportunity to attack from either side of the substrate. Even though a mixture of configurations is often obtained in an Sn1 reaction, typically we'll observe more of the inversion product because the leaving group can form an ion pair with the carbocation, making it more difficult for the nucleophile to attack from that side. We're going to take all of these different variables and factors and weigh them in to try to figure out what type of reaction is going to occur when we're given a substrate and conditions. In many cases, we'll obtain a mixture of products which include both the elimination and the substitution. For some substrates and reaction conditions, we'll only have one mechanism that occurs. And in order for us to understand these reactions and utilize them to transform alkyl halides into desired compounds, we need to be able to predict all of the potential products that will form in a given reaction, as well as identify which will be the major or minor products. So in order to successfully predict these products, there's a three-step analysis which we can perform. And this three-step analysis will look at all of the different variables possible. First, look at the function of the reagent. Do we have a strong nucleophile? Do we have a weak nucleophile? Do we have a strong base? Do we have a weak base? What type of solvents do we have? Do we have an aprotic solvent or do we have a protic solvent? Then, after we've looked at all of the reagents in the reaction conditions, we should look at the substrate. Is the alkyl halide on a primary, secondary, or tertiary carbon? If a carbocation were to form at the position where the alkyl halide is located, would it be able to undergo rearrangement? And then finally, we'll want to consider any relevant regiochemical and stereochemical requirements to help determine the correct structure of the potential products. A Sn2 reaction is going to be favored in the presence of a strong nucleophile. An Sn1 reaction is going to be favored in the presence of a weak nucleophile. An E2 reaction will be favored in the presence of a strong base, and an E1 reaction will be favored in the presence of a weak base. The table located at the bottom of the screen, it does a relatively good job at summarizing the weak bases, strong nucleophiles, and weak nucleophiles, as well as what type of reaction they're likely to occur. During step 2, we're going to be looking at the structure of the substrate. Is it primary versus secondary versus tertiary? And then we can compare that information to the type of reagent that we have. And this will help us narrow down the potential reactions that can occur. Please keep in mind that in general, primary substrates are almost always going to be doing E2 and Sn2 reactions unless they have the ability to rearrange. And tertiary substrates are often favored to do Sn1 or E1 reactions. They can also do E2 reactions in the presence of a strong base, but they will never do Sn2 reactions. For an Sn2 reaction, we're going to observe a single product, which will be inversion of configuration at the alpha carbon. For an E2 reaction, there's going to be potentially several different alkene isomers that can occur. So we want to start by drawing all of these alkene isomers. And these will result from different beta hydrogens that can have an anti-periplanar relationship to the leaving group. Then, if we have a bulky base, we can identify that the Hoffman product is a major product. Or if we're using a non-bulky base, that the Zaitsev product is going to be the major alkene isomer, which is also the most stable isomer. For an Sn1 or E1 reaction, we're going to want to start by drawing the carbocation intermediate and then identifying if it can rearrange. If not, then we'll attach the nucleophile to the carbocation and obtain a mixture of both the R and S product. And finally, for an E1 reaction, we'll also draw the carbocation that's formed, identify it can rearrange, and then draw all the possible alkene isomers that would result from elimination of beta hydrogens. All possible alkene stereoisomers will form, but the major product will always be the most stable alkene. Let's take a look at the following reaction. Here we have a secondary alkyl bromide being treated with sodium hydroxide. Which products do you think we'll be able to obtain from this reaction? Well, in the first step, let's look at the reagents. We have sodium hydroxide, which is both a strong base and a strong nucleophile. This means that Sn2 and E2 reactions will be favored with this reagent. Next, we can look at the substrate, which is a secondary halide, and it also does not have the ability to rearrange to a more stable carbocation. So, Sn2 and E2 will occur, but elimination will dominate because of the somewhat sterically hindered substrate. Finally, we need to consider the regio and stereochemical requirements. For the Sn2 product, this is fairly straightforward. It's going to attack from the backside of the leaving group and result in inversion of stereochemistry to form this alcohol Sn2 product. For the elimination reaction, it becomes a little bit more complicated. We now have multiple different hydrogens that can be eliminated. Elimination of HA is going to lead to the trans alkene. Elimination of HB is going to lead to the cis alkene, and elimination of one of the hydrogens on the methyl group will ablate the stereocenter and lead to this terminal alkene. The most stable alkene of these three products is going to be the trans alkene, and this will also be the major product. The beta hydrogen in this position is more sterically hindered but leads to a more stable product. Since we're using a small base or non-bulky base, we will obtain this more stable product as our major product. So this reaction will yield a total of 4 products, with the transalkene being the most stable product. There are a variety of other substrates that can be used as good leaving groups for substitution and elimination reactions. Drawn here are a few common leaving groups that are used. We can use the mesylate group, the tosylate group, and the triflate group. All 3 of these functional groups have one thing in common, which is their ability to stabilize the negative charge on oxygen that's produced as they leave through resonance. And the resonance of that negative charge can all 3 oxygens can stabilize that negative charge, and we can draw different resonance structures. The pKa value for the corresponding acids for these molecules are all very low. So these are very strong acids, which makes them relatively good leaving groups. Here is a 5th reaction that we'll learn in this chapter, which is the synthesis of a sulfonate from its corresponding alcohol. So we can take an alcohol and treat it with tosyl chloride and pyridine as a base to form an alkyl tosylate. An alcohol is a relatively poor leaving group. However, we can convert it to a good leaving group using this reaction. We can take an alcohol, convert it with tosyl chloride and pyridine to its tosylate, and now we have a good leaving group that can be converted to other molecules using an Sn2 reaction. Since we can convert alcohols to tosylates, we now have a large number of products that we can form from alcohols. So if you want to envision what type of compounds you can synthesize from an alcohol or an alkyl tosylate, treat them the same as we would an alkyl halide. It just might take an extra couple of steps. We can still, with a strong nucleophile or base, convert to the E2 or the Sn2 product on a primary tosylate, and from a secondary tosylate we can convert to the E2 elimination product or the Sn2 substitution product. Alcohols can also be used in substitution and elimination reactions and used on starting materials as starting materials to make alkyl halides and alkenes. A 6th reaction that we'll learn in this chapter is to convert a primary alcohol to a primary bromide using HBr as a strong acid. This strong acid both protonates the alcohol in the first step and then acts as a nucleophile in the second step, whereas we have water as a good leaving group. So we can convert alcohols to a primary alkyl halide using HBr as a reagent. Depending on the substrate, the mechanism for this reaction will either be Sn1 or Sn2. We can also use concentrated sulfuric acid to convert a tertiary alcohol to an alkene using an E1 reaction. We'll protonate the alcohol, and then water will act as a weak base. First step, protonation, then the leaving group leaves, forming the carbocation, and then water acts as a weak base in an E1 mechanism to form the alkene product. So I know this picture summarizes a lot of information in one slide, but as we move into synthesis, which is going to be the application of each of these individual reactions to form new molecules, convert one type of structure to another, sometimes through multiple transformations in a row, we need to be able to kind of have all of these different reactions in our toolbox. And one of the easiest ways to start is from an alkyl halide. An alkyl halide is going to give us access to all of these different functional groups through either substitution and elimination reactions. I strongly suggest making flashcards for each of these transformations, so that way you can compare them to the entire web of potential reactions as you memorize them. As we learn more reactions, we're going to expand upon the size of this web. In order for us to be able to identify, for example, if we want to make a specific compound, we have to remember all of these different reactions that we could use to convert one material to another.